Hello friends, hello Tricia. Friends, last class we started with the light source material like light emitting diode is one kind of the light source material. This I have discussed on the last class. Okay, uh, so in order to fabricate the LED or the laser source, you need the different kinds of the semiconductor devices. Okay, so normally you can use the direct band gap semiconductor that is normally used for the light source material. Okay, so here you can see it is mentioned that the direct band gap semiconductor that is mainly used for the direct band gap semiconductor means there is a conduction band minima, so there is a conduction band minima and the valence band minima both will be in the same point. Okay, no need to change the momentum for the direct band gap. For indirect band gap, the conduction band minima and the valence band maximum both will not be at the same point, so they can release the phonon instead of the photon. So for getting the good light source emitting diode, okay, so for that you need the direct band gap semiconductor where the electron and hole can easily recombine with the without the help of the any other material or any other change of the momentum for case of the direct band gap material. Normally, we use the radiative recombination for getting the high optical efficiency. Okay, the high optical means high radiance power. For getting the high radiance power, we need the radiative recombination. Radiative recombination means in case of the indirect band gap semiconductor, when the electron will go from the upper band to uh, lower band or the excited state to the ground state, they can release the photon. Because that recombination, that process is called the radiative recombination. When the electron will come from upper state to suppose it's the upper state and this is the lower state. So sometimes it will happen that it will not come directly to the ground state, it will come to the other state, and from the other state to again it will come to the ground state. So in this process, so there is a release of the phonon. That combination is called the non-radiative recombination. That means the recombinations take place. Due to this recombination, there is a release of the phonon instead of the any radiation. So that's it. That concept is called the non-radiative recombination. And the group 3,5 compound, you can see the group 3,5 material semiconductor. These are mainly used for the direct band gap semiconductor. And one of the most common indirect band gap semiconductor name is the silicon. Silicon is the one of the most common. So you can see silicon can be used for the various purpose, various electrical applications or the semiconductor IC applications. But if you want to think about the light devices or detector, silicon is not the suitable for those devices. Normally, the group 3,5 compound. Nowadays, the various organic materials are also used for designing the light source material. The group 3 materials, these are the aluminum, gallium, indium, phosphide, arsenic, Sb. These are without composition and co-deposition. One composition you can use you can design the light source material. And so this kind of the alloy can be made for the light source for LED, the gallium 1 minus X and 1 minus X and the aluminum X and arsenic. Okay, so this is the molar ratio. If you change the molar ratio, the band gap will also change. The ratio of the X aluminum arsenic and the aluminum gallium arsenide, that defines the band gap of the particular material. Normally, the X would be designed such a way that it can emit the 850 nanometer wavelength light. Okay, there is a formula for that. Now, here you can see that if you change the aluminum molar fraction, the band gap will like this way it will change. If you increase the molar fraction, if you increase the value of X, the band gap will also increase like that. Okay, and if you want to plot the wavelength versus the radiated output for a light source material or LED, so you can get the little bit broad spectrum response. Okay, so it can emit the light from the 770 to 850 nanometer light with the and the maximum radiation will be at suppose 810 nanometer. It has maximum radiation intensity. Okay, so the band gap corresponds to 800 nanometer wavelength. Okay. Yes, this formula already we know that is a relationship between the wavelength of the photon and the band gap of the material. Okay, so if suppose the whatever photon is produced from the device, that photon energy should be greater than the band gap of the semiconductor. Okay, then E should be greater than Eg. Eg is the band gap of the semiconductor. The photon energy photon energy will be calculated as a Hc by lambda. From the lambda, you can calculate the E. That E should be equal to the band gap of the semiconductor or greater than of the semiconductor. Okay, so if if band gap is the suppose 1 electron volt, so from one by using the Hc by lambda, you can calculate E is equal to Hc by lambda. You can calculate the lambda, that is wavelength of the light. You can calculate. This is the most familiar formula, most popular formula, and so if you put the Hc value, then the value will be like that 1 point. So Eg same, the Eg is equal to 1.24 by lambda, while lambda is in the micrometer and the Eg is in the EV. So these are the band gap for the silicon, gallium arsenide, germanium, indium phosphide. So these the video format, the gallium arsenide, indium phosphide, and gallium arsenide. These three kinds of the material are most widely used for the light material. Okay, so this is a formula. So suppose I told gallium aluminum arsenide 1 minus X aluminum X arsenide. So for that, if you put the, if you consider some X value, suppose 0.37. So if you put the this is the formula. So how the X change with the band gap. So if you put the value of X, the 0.37, you can get the band gap of the particular material. Okay, this is the formula. And if two different kinds of the molar ratios are there, that is 1 minus x, x, y, 1 minus y. So first there is a relationship between x and the y. Then you need to calculate the band gap for where the band gap is related to y only, not in the x. Indirectly, it is related to s. So for this kind of the material, if you want to calculate the band gap, we need to use this formula. So here you can see the lattice parameter versus band gap. This is the graph. Now we last class we discussed about the two different kinds of the light emitting diode. One is the edge emitter, another is the surface emitter. Okay, so here you can see this the surface emitter. The surface emitter means the LED comes from the photon that comes from the surface of the device. Okay, from the substrate side. So it has a wider area, and the fiber is also not coupled properly. Okay, so for that the beam area will be more for case of the surface emitting LED, and for case of the edge emitting LED, so it come from the edge of the device. Okay, it come from the edge of the device. The light come from the edge of the device. So from the edge emitting diode, you can see the narrow spectrum response. For different application, you can use the surface emitting diode, and sometimes you have to use the edge emitting diode. This depends on the different applications. Now come to the quantum efficiency. Quantum efficiency and the LED power. So LED power, that is directly related to the quantum efficiency. Normally quantum efficiency that normally defines the internal phenomena of the material. Okay, internal phenomena of the material. Right. So quantum efficiency normally, how much, suppose what is the phenomenon of the LED. So you need to inject the electron and the hole. The electron hole should be recombined, and which will produce the photon. So quantum efficiency means, so how many numbers of the electrons are hole injected. Suppose you have injected the 100 amounts of the electron and photons, or electron and holes, 100 amount of electrons and holes. Is from the 100 amount of electrons and holes, if the 100 amount of electrons and holes are produced uh, photon, then your efficiency will be high. Okay, the ratio between the number of photons generated from the device and the number of the photon number of the electrons and holes are required to produce the photon. So ratio between the electron and holes and to the number of photons produced. So normally I told that the quantum efficiency, the recombination, that will be divided into two parts. One is the radiative recombination, or it is the non-radiative recombination. Radiative recombination and non-radiative. So we suppose 100 amounts of electrons are injected. Okay, 100 amount of electrons are injected. From the 100 amount of electrons, there will be a chance that 20 amount of electron will produce the non-radiative recombination. Okay, and the 80 amount of the electron will produce the radiative recombination. Okay, so in every device there will be some defect. Due to defect, we will have the non-radiative recombination. That means the suppose again for the, so if the 80 amount of electrons have produced the 80 amount of photon, okay, 80 amount of the photon. So those 80 amount of photon, due to the device structure and reflective index, those 80 amount of photon will not coming out and will not produce the light. So some photon will be absorbed by the device. So due to that also there will be different kinds of deficiency. One is the internal efficiency, another is the external quantum. Internal quantum efficiency is related to radiative and non-radiative recombination, and the external quantum efficiency that is related to the reflecting index of the material, how much photons after production of the photon, all the photons are coming out or not, that depends on the this thing only. Okay, so there is one term, the carrier lifetime, and the N naught, the initial injection of the electron density, that is electron. How many electrons are injected, that density divided as the N naught. The tau, the carrier lifetime, after injection of the electron, the electron hole should be recombined. The duration is called the carrier lifetime. So here I am going to explain one derivation for regarding the quantum efficiency. Normally the internal quantum efficiency that I told, that is normal totally related to the radiative and the non-radiative recombination. So the radiative recombination divided by total recombination. Okay, so RR is the radiative recombination, RNR is the non-radiative recombination. There is a radiative recombination lifetime. Okay, so N is the number of excess carrier produced due to the injection of the atom. So the radiative recombination lifetime, that is equal to the number of injected electron divided by radiative recombination rate. The non-radiative recombination, so how much time required to produce the recombination, to induce the recombination. Okay, so N is the injection of the electrons. So it will take some time to recombination, for recombination. So suppose it is radiative recombination and the non-radiative recombination. So the lifetime, that lifetime is the tau r and the tau nr. So N by RR and N by RR. Okay. So the internal, so if you put, suppose if you instead of RR, if you put the N RR instead of RR, if you put the N by tau r, again here instead of RR you are putting the N by tau r. Okay, here you are putting the N by N by tau nr. Okay, so if you do some substitution, you can get this one. Okay, if you do substitution, you can get, so after substitution from this equation to this equation, you will get this one. Okay, after substitution from this to this, you will get. Okay, this is in the form of the lifetime, carrier lifetime. This is in the form of the radiative recombination. And so if you want to think the total lifetime, okay, the total entire bulk recombination lifetime, that is related to this way: 1 by tau is equal to 1 by tau r plus 1 by tau nr. Okay, this is the bulk recombination lifetime that consists of the radiative recombination lifetime, non-radiative recombination lifetime. So this equation already I told, and again instead of tau nr. Okay, so here you can get a one relationship between tau r and tau nr. Okay, so suppose what relationship we get, suppose 1 by tau is equal to tau r tau nr divided by tau nr plus tau r. Okay, and then if we replace the nr, okay, if we replace the nr with this, if you common the nr, what will happen? So 1 by tau is equal to 1 by tau r by tau nr, like that. So in this way you will get this equation. Okay, I'm not substituting this one. So if you interrelate this equation and this equation, okay, if you interrelate this equation and this equation, these two equation, okay, so you will get this one, tau by tau r. Okay, internal efficiency will be tau by tau r, right? So then next step is that normally that I by Q. What is the I by Q? I is the how much current produced, Q is the charge of the electron. Okay, so I by Q, that gives the total number of electrons injected. Okay, total number of electrons injected. That means I by Q. So you are giving some current. Due to that, you are getting some there's some induction of the electron and the hole. Okay, those electrons hole will be responsible for the radiative recombination and the non-radiative recombination. So that's why the I by Q is equal to R by R N R. Okay, right? So again, if we substitute this equation, okay, if we substitute this equation with the previous one, what I told, there is a relationship between N internal and R and R. Okay, So if you substitute those equations, you will get a this one. Okay, ready to recombination rate is equal to internal quantum efficiency into I by Q. Okay, now there is a this is a relationship between quantum efficiency and the radiative recombination. Now if you want to calculate the optical power, okay, input optical power. Okay, now we want to calculate the input optical power, that is equal to, if you multiply the radiative recombination with the h nu, if you multiply the radiative recombination with the flux, that is the h nu. Okay, so you will get a this relationship. Okay, that is the relationship between the power and the internal quantum efficiency. Normally that the radiative recombination and non-radiative recombination, this you cannot calculate, okay, from the device. You can calculate the efficiency, you can calculate the current, you can calculate the efficiency. So from that you can calculate the power. Okay, and you know the value of h, and also you know the optical frequency. Okay, and you know the electron q. So if you know those this value, if you know the eta efficiency, if you calculate from the device, you can calculate the power, how much power is to be produced from the LED. Okay, so that is the external quantum efficiency. The derivation is not important. So the external quantum efficiency, that is equal to 1 by eta, not eta, it is n. It is another term, that is the reflective index. Okay, the reflective index of the semiconductor material, n into n plus 1 whole square. That is the internal quantum efficiency. The total optical power will be external quantum efficiency. External quantum efficiency and the internal power, P internal divided by n into n plus 1 square. So what I told, that total quantum efficiency, so how much photons are produced from the device. Those photons are not responsible for, these photons will not be coming out from the device. Okay, some photon will be absorbed by the material, that is also due to the reflecting index. That's so the external quantum efficiency, that is related to the reflecting index of the material. So then, so if you want to calculate the total optical power, how much photons are produced, or total optical power if you want to calculate, then it will be calculated P is equal to n external into P in, that is equal to P in by n into n plus 1 whole square. Okay, so these are related to quantum efficiency and the LED power, and some more points are there related to LED power, and the one to numerical I will show you. Then the optical bandwidth also, the modulation bandwidth for the LED, that also I will discuss in the coming lecture, and followed by the laser, introduction to laser. So please like, share and subscribe my channel. Thank you.